So, when British sailors, centuries ago, contracted scurvy on these long voyages, the most horrifying symptom wasn't actually just, the fatigue or the bleeding gums.
Right, the classic symptoms we always hear
Yeah,
about.
exactly. It was actually the fact that scars from wounds they had suffered decades earlier, like wounds that had been perfectly healed for years, would suddenly just begin to dissolve and tear back open.
It's such a horrifying image to think about.
It really is. And the underlying biological mechanism behind why those scars literally melted away is exactly why the chicken breast and the whey protein you ate today might be quietly starving your body's structural foundation.
Yeah, and it is a really profound realization. I mean, we have this tendency to think of our bodies as static structures once we reach adulthood. You build the house and the house just stands there.
Right, the work is done.
Exactly. But your connective tissues are actually in this constant dynamic state of being dismantled and rebuilt. And if you remove the specific raw materials required for that rebuilding process, well, the structure eventually collapses under its own weight.
And that's exactly what we are going to explore in this deep dive today, because we've gathered this amazing stack of sources, ranging from NIH biochemical research to clinical dietary guidelines for wound healing.
Some really fascinating stuff in there on osteoarthritis, too.
Yes, definitely. And the mission of our deep dive today is to answer this surprisingly complex question. Can low protein intake fundamentally affect how your body rebuilds its collagen? Because, we always hear about collagen in the context of like expensive anti-aging skin creams or beauty supplements.
Right, it's heavily marketed.
Yeah. But what these sources show is that standard modern dietary habits, even the ones we consider incredibly healthy and high in protein, are fundamentally mismatched with what our bodies actually need to hold themselves together.
It's true, because we tend to view protein as a monolith, right? You look at a nutrition label, you see 25 grams of protein, and you just assume your body has everything it requires for every tissue type.
Right, like if I'm eating a standard high-protein diet, say a chicken breast, or slamming a whey protein shake after the gym, isn't protein just protein? Why do I need to worry about collagen rebuilding specifically?
Well, to understand why standard protein isn't enough to protect your joints and your healing capacity, you really have to look at the unique molecular architecture of collagen itself. It's very different from muscle protein.
Okay, let's get into that architecture, because just to establish the sheer scale of what we are talking about, collagen isn't just some niche beauty ingredient. It actually accounts for somewhere between 25 and 33% of the total protein mass in a mammalian body.
Yeah, up to a third of your entire protein structure is just this one specific type of material.
It's just wild.
It is. And, scientists have classified 28 different types of collagen so far.
28. I didn't realize there were that many.
Yeah, but types I through EV are really doing the vast majority of the heavy lifting. And type I is the undisputed heavyweight here. It makes up over 90% of the collagen in your body.
Wow.
Yeah, it provides the primary structural framework for your skin, your bones, tendons, ligaments, and this is crucial, even your blood vessels.
So when you look at type I collagen under an electron microscope, you see this incredibly intricate rope-like structure, right? It's called a triple helix.
Right, the triple helix.
So it's basically 3 separate polypeptide chains, which are known as alpha chains, and they're coiled super tightly around a central axis. It honestly looks almost like DNA,
Yeah.
but with 3 strands heavily braided together instead of 2.
Exactly. And the reason it can form that specific, incredibly dense braid comes entirely down to its amino acid sequence. Collagen is built on a very rigid, relentlessly repeating pattern.
Okay, what's the pattern?
It goes glycine, followed by proline, followed by another amino acid, which is often a modified version of proline called hydroxyproline. But the absolute non-negotiable rule of this structure is that every third amino acid must be glycine.
Every single third one.
Every third one, without fail.
And there's a pure geometric reason for that, isn't there? Because glycine is the smallest of all the amino acids. Its side chain is literally just a single hydrogen atom.
Exactly. It's tiny.
So if you try to force any other amino acid into that third position, its side chain is just too bulky. It creates what chemists call steric hindrance, right?
Yeah, steric hindrance. Basically, the 3 strands physically cannot pack tightly enough together. They bump into each other.
So the rope loses its tensile strength.
Precisely. The triple helix relies completely on that tiny profile of glycine to fit into the crowded interior axis of the coil. Without glycine at every third position, the strands just kind of remain loose, and the molecule absolutely cannot withstand the mechanical stress of normal human movement.
Okay, so if we look at this from a dietary perspective for the listener, If you were building a brick wall, the muscle meat you eat, like your standard steak or chicken, might provide the bricks, but collagen is the mortar holding it all together.
That's a great way to look at it.
And within that mortar, glycine is the essential sand that makes it all stick together. But here is the massive disconnect I found when reading through these sources. I was looking at the amino acid profile of standard whey protein isolate.
Oh, yeah. The numbers are shocking.
They really are.
Yeah.
Whey is incredible for triggering muscle protein synthesis because it's packed with branched-chain amino acids, like leucine. But whey protein only contains about 2% glycine.
Just 2%. And to put that into stark perspective, remember that the collagen triple helix requires a composition that is roughly 33% glycine, 17% proline, and 10% hydroxyproline.
Right, so whey is functionally useless for synthesizing connective tissue.
Basically, yeah.
And it contains absolute zero hydroxyproline.
Zero, nothing. And plant-based proteins run into the exact same bottleneck. Like a high-quality pea or soy isolate will give you the essential amino acids you need for general metabolic health, sure.
And muscle maintenance.
Right, muscle maintenance. But they are dramatically low in glycine and proline, and again, completely devoid of hydroxyproline. Even the standard lean muscle meats that completely dominate modern diets, the boneless, skinless poultry or lean beef cuts, have surprisingly low concentrations of these specific structural building blocks.
Which brings us to a really fascinating biochemical bottleneck in the research called stoichiometric restriction.
Yes, this is the core of the issue.
Essentially, there is a hard mathematical limitation on how much glycine the human body can manufacture on its own from other substrates. Because for decades, nutrition textbooks actually classify glycine as a non-essential amino acid, right?
Yeah, they operated on the assumption that because our metabolic pathways can synthesize it, we just don't need to consume it in our diet.
But that classification is completely misleading, isn't it?
It's one of the most persistent and damaging misunderstandings in modern nutrition, honestly. When biochemists actually sat down and calculated the specific rate limits of our synthetic pathways, like primarily in the liver and kidneys, and they compare that to the amount of glycine required for daily collagen turnover.
The math simply did not work out.
It didn't work at all. The body's synthesis capacity falls drastically short of our actual daily needs.
I want to linger on the magnitude of this shortfall for you listening because the numbers are staggering. An average 70-kilogram adult runs a daily glycine deficit of roughly 10 grams.
10 grams a day.
Just to maintain baseline collagen synthesis. Because your body naturally degrades and rebuilds its structural matrix every single day, and a huge fraction of the glycine released during that degradation pathway is just excreted or used for other metabolic processes.
Right. It isn't available for reuse. It's gone.
And a standard modern diet, heavy in muscle meats and processed proteins, might only supply, 1.5 to 3 grams of glycine?
Yeah, maybe 3 on a good day. So you are running a massive chronic deficit constantly.
So to close that gap, you actively have to consume connective tissue. You literally have to eat the skin, roast the bones, consume traditional bone broths, or utilize highly concentrated collagen peptide supplement.
Exactly, because if you are just drinking a whey shake and eating a chicken breast, it's like trying to build a house and the hardware store drops off a massive pile of wood at the construction site, but they completely forgot to send the nails.
Right. You have the materials for the muscle, but you are leaving your connective tissue starving. So, okay, if we are chronically operating at a 10-gram deficit, what happens when the system is suddenly thrust into a state of acute stress? Say you undergo a major surgery, or suffer a severe burn, or even do a highly invasive laser skin resurfacing treatment.
Acute trauma is the ultimate stress test for your collagen production pathways. When the skin or structural tissue is breached, the body enters this intense hypermetabolic state.
It goes into overdrive.
Total overdrive. It perceives an immediate, life-threatening emergency and begins marshaling every available resource it can find to lay down a new collagen matrix and seal the wound.
And this is exactly why clinical dietary guidelines for wound healing dictate a massive spike in protein intake, right? They recommend anywhere from 1.25 to 1.5 grams of protein per kilogram of body weight.
Yes, the body urgently needs raw materials to generate new tissue. And not just skin, but it has to synthesize the localized blood vessels necessary to deliver oxygen to the injury site.
But, and this is the scary part, if your dietary protein intake is generally low or specifically deficient in these collagen precursors like glycine, the body essentially panics.
It really does. It enters a catabolic state, which means it starts breaking down its own healthy muscle tissue. It literally cannibalizes itself just to scavenge whatever trace amounts of glycine and proline it can harvest to feed the wound.
Wow. And the cellular mechanics of this are incredible to visualize. Translating genetic code into a collagen protein is intensely demanding because that repeating sequence is so heavy in proline and glycine.
Right. Remember that rigid pattern we talked about?
Yeah. So during the translation process, if the cellular machinery, the ribosome, is moving along the mRNA strand and it cannot locate an available proline molecule,
Mm.
the entire apparatus literally stalls.
The translation process just grinds to a halt. If the specific amino acid is unavailable, the ribosome pauses, and if the delay is too long, the peptide chain is often aborted entirely.
So the cell physically cannot construct the tissue.
No, it can't. It doesn't matter how much leucine or valine you have floating around from your expensive whey protein. If you lack proline, the structural matrix is not getting built.
But wait, if this mechanism dictates acute healing, what does this mean for chronic degradation? Because we have this deeply ingrained medical and cultural narrative that joint pain, stiff knees, and just general immobility are just the mechanical realities of getting older.
Yeah, the classic wear and tear diagnosis.
Yeah. Right. Doctors tell patients it is simply wear and tear on the cartilage over time. But looking at this biochemical deficit, are we completely missing the mark? Like, is a massive portion of what we categorize as aging actually just the physical manifestation of a decades-long nutritional deficiency masquerading as time?
The research strongly points in exactly that direction, particularly when we look at osteoarthritis.
Okay, tell me more about that.
Well, osteoarthritis is characterized by the progressive degradation of articular cartilage, which relies heavily on type 2 collagen for its shock-absorbing properties. The specific cells responsible for maintaining that matrix are called chondrocytes.
Chondrocytes, got it.
Right. And the emerging hypothesis in these papers is that osteoarthritis isn't merely mechanical friction, it is a fundamental metabolic failure. It is driven by the chronic inability of those chondrocytes to synthesize enough new type 2 collagen to replace what is naturally lost to friction.
Because they're starving for glycine. I was looking at the in vitro studies on this, and it blew my mind. When researchers took bovine articular chondrocytes and bathed them in a medium with high concentrations of glycine, their synthesis of type 2 collagen completely exploded.
The numbers were incredible.
It increased by up to 200%. So the limitation wasn't the age of the cell, it was just the absence of the raw material.
Precisely. When you remove that stoichiometric restriction we talked about, the cells immediately upregulate their repair mechanisms. The researchers concluded that targeted glycine supplementation, or a diet rich in connective tissue, could be a foundational therapeutic strategy for cartilage regeneration.
That is huge.
It is. Think about it. If you run a 10-gram deficit of the primary structural component of your joints every single day for 30 or 40 years, the structure is guaranteed to erode. Time is just the variable. The deficiency is the actual mechanism.
Okay, so we've established that we absolutely need the raw materials. We need the glycine, the proline, the bone broth, and the skin. But there is a crucial secondary layer to this architecture that brings us all the way back to our sailors suffering from scurvy in the intro.
Ah, yes, the construction crew.
Right, because even if you flood your system with the perfect ratio of amino acids, the collagen triple helix still cannot properly form and stabilize without a very specific crew of enzymes to assemble it.
Because having the bricks doesn't mean you have a wall. You need the enzymes to lay the bricks, and the master architect in this biological process is an enzyme called prolyl-4-hydroxylase.
Okay, prolyl-4-hydroxylase. How does that actually interact with the collagen chain?
So, as the ribosomes are assembling those polypeptide chains, they don't immediately insert hydroxyproline, they just insert standard proline.
Okay.
Once the chain is partially constructed, prolyl-4-hydroxylase moves along the sequence and chemically modifies specific proline residues, adding a hydroxyl group to them. This post-translational modification is what officially converts proline into hydroxyproline.
And why is that hydroxyl group so essential to the final product? Like, why does it matter?
Because that hydroxyl group allows for the creation of intramolecular hydrogen bonds between the 3 separate chains of the helix. It basically acts as the chemical superglue.
Oh, I see.
Yeah, without extensive hydrogen bonding, the triple helix is incredibly unstable. In fact, without hydroxyproline, the collagen molecule will literally denature and melt apart at normal human body temperature. It cannot maintain its solid structure at 37 degrees Celsius.
Wait, really? It just melts.
It literally unwinds and melts.
Okay, so this enzyme is non-negotiable for stable tissue. But proline-4-hydroxylase is what biochemists call an alpha-ketoglutarate-dependent dioxygenase, which basically means it cannot perform this chemical modification on its own, right?
Exactly. It is completely reliant on specific micronutrient cofactors to keep its active site functioning.
So what does it need?
It requires a steady supply of oxygen, alpha-ketoglutarate, which is generated naturally during cellular respiration, as well as iron and vitamin C.
Vitamin C being the big one here.
Right. There are also distinct roles for trace minerals like zinc and silicon in broader collagen maturation and cellular proliferation, but vitamin C is the absolute linchpin for this specific hydroxylation process.
Because vitamin C acts as an electron donor,
Right.
right? It keeps the iron molecule situated in the enzyme's active site in its reduced state, which is what allows the enzyme to continue functioning.
Yes. Without vitamin C, the enzyme oxidizes, it shuts down, and absolutely no hydroxyproline is generated.
Which brings us right back to the sailors and the sheer terror of scurvy. Scurvy is not just a disease of fatigue. It is the total systemic failure of collagen maintenance
Exactly.
because the body's in a constant state of turning over its collagen. So the old scar tissue on a sailor's arm from a sword wound 10 years prior is naturally being broken down, but because the sailor lacks vitamin C, the new collagen being synthesized to replace it cannot be hydroxylated.
Right, it can't form those essential hydrogen bonds.
So the new collagen is fundamentally unstable. It literally melts at body temperature. The structural integrity of the tissue drops to zero, and the previously healed wound simply splits back open. The body loses its ability to hold itself together.
It is such a visceral illustration of the concept.
It really is. So basically, eating muscle meat is like dropping off the raw materials at the site. But vitamin C, iron, and zinc are the tools the workers absolutely need to cure the mortar. If you don't provide the tools, the mortar never sets, the helix denatures, and the tissue remains totally vulnerable or degrades entirely.
And if you synthesize the data across all these domains, from the clinical wound healing parameters and the ribosomal translation mechanics to the chondrocyte studies and the enzymology of proline-4-hydroxylase, the conclusion is just undeniable.
Yeah, the evidence is overwhelming.
Low intake of collagen-specific amino acids, compounded by a lack of micronutrient cofactors, severely impairs the human body's ability to maintain its physical structure.
So if you were listening to this and you want to heal effectively from a surgery, or maintain the elasticity and resilience of your skin, or protect the shock-absorbing cartilage in your joints, you really have to look past the generic total protein number on the back of a package.
You absolutely do. You must specifically feed the tissues you are trying to support with glycine, proline, and the vital cofactors that stabilize them. You have to respect the distinct biochemical requirements of your connective tissue.
Which leaves us with a highly provocative concept to examine regarding our modern food systems. Because for nearly all of human evolutionary history, our ancestors practiced nose-to-tail consumption.
Oh, yeah. Nothing went to waste.
They didn't just eat the skeletal muscle of an animal. They boiled down the bones for broth, they ate the cartilage, the skin, the tendons, and the organs. They naturally consumed a high-glycine diet that was perfectly calibrated to support human connective tissue turnover.
And compare that to today.
Right. Today, we have engineered a diet built almost exclusively around the most convenient, most sterile muscle meats. Boneless, skinless breasts, lean ground beef, and highly refined whey isolate.
We stripped out all the structural proteins.
Exactly. And if our physiology requires a massive daily influx of these specific structural proteins, and we have systemically removed them from our plates, well, perhaps the modern epidemics of chronic joint degradation, osteoarthritis, and poor tissue resilience aren't just unavoidable symptoms of time and aging.
It makes perfect biological sense.
Perhaps they are the direct, measurable consequence of fundamentally abandoning the structural building blocks our bodies evolved to rely on. It is certainly something to factor into your calculus the next time you are deciding between another scoop of isolated whey protein and a steaming mug of traditional bone broth.